Welcome to my video in the seminar Planetary Space Exploration on the topic Kalman filter-based SLAM. The primary source of this video is the book Planetary Rovers, Robotic Exploration of the Solar System by Alex Ellery. The chapter of this topic is 9.4 Kalman filter-based SLAM. Starting with the content of this video, we will first answer the question what Kalman filter-based SLAM is, and in particular what SLAM means. Then we will look at an example video of a rover performing SLAM. Then we will answer the question what a Bayesian filter is, or a bias filter. Then what a Kalman filter is. And in the end we will look at other solutions for solving SLAM other than with a Kalman filter. What is Kalman filter-based SLAM? The short term SLAM means self-localization and mapping, or more accurately, simultaneous self-localization and mapping. There exist multiple problems that have to be addressed in SLAM. Since our current partial world model at a time t was built with uncertainties introduced by noisy sensor readings, it is challenging to correlate the new readings at time t with the world model. In addition to that, a rover performing SLAM might also move between readings, and therefore the coordinate system of older and newer sensor readings might be shifted and/or rotated. This has to be taken into consideration to relate them back to each other. Looking at a rover, there are also multiple different sensors involved to perform SLAM. For example, odometry measurements that include the angle and rotation speed of wheels and a laser sensor measurement. This sensor fusion also is addressed in SLAM. Looking at the two pictures, the first clearly shows how imperfections in our model can propagate when no correction algorithm is used. We need to account for uncertainty to improve our map building. The second picture on the right clearly shows how effective SLAM can be. Most of the imperfections in the laser scanner data is now corrected, and the hallway that the rover passed through is clearly visible. The rover, in this case controlled by a human operator, is starting at a position and gets his first laser scan measurements. As it is driving, it explores more and more parts of the unknown environment, and the map expands. The new scans are matched against the existing map to perform localization. For some applications, this map of the unknown environment might be the requested information, but other applications might also use the map to perform further path planning. This now leads us to the next question. What is a bias filter? To implement SLAM, a bias filter can be used. We have a prediction step which estimates the motion and a correction step where the measurement is updated. In the prediction step, we have a convolution between two probability density functions. The first probability density function includes the information where I am at step k. The second probability density function includes our previous believed measurements. In the correction step, we now convolve our prediction with another probability density function. This probability density function is our observation model. Let's look at an example of self-localization in a previously drawn map. Obstacles and walls are indicated by black lines. Our previous rover position is indicated by the blue dot, and the yellow arrow points towards the predicted position after taking the motion model into consideration. The red arrow, however, points to another position based on the observation model. A laser scanner on the rover might have measured that the obstacles in the map appear to be at a different distance than they would be if we were to believe the motion model. After calculation with the two probability density functions, we could now end up with a position like the one indicated by the green arrow. This recursive algorithm then of course is used when a new time step is reached. This can of course also be used not only for previously drawn maps, but also for unknown environments where self-localization and mapping are performed at the same time. For linear systems with normally distributed variables, the bias filter actually equals the Kalman filter, which brings us to the new topic: what is a Kalman filter? The Kalman filter, same as the previously described bias filter, is recursive. Therefore, it accommodates for all previous measurements. This contribution of previous measurements on the current calculation, however, decreases exponentially over time. The filter is an optimal solution for perfectly linear systems with perfectly Gaussian noise. The mean square error of the estimate is minimized, which results in the optimal estimation of the state. One of the advantages of this algorithm is that no training is required. It's just pure math. Speaking of which, let's take a look on how to mathematically model our previously shown rover in terms of Kalman filter formulas. The example used here is from the book. We start by defining our three-dimensional state vector, x of k, which holds the two-dimensional position, x and y, and the heading, in our case, jaw angle phi. Next, we define our kinematic equations, which are used to predict the state using velocity, here indicated by v, and also steering inputs indicated by phi. The variable L represents the distance between forward and rear axes. Let's look at our control inputs. We have a two-dimensional vector u of k, which consists of the velocity v of k and also the steering angle w of k. Those two inputs combined with our motion model are equivalent to the prediction step in the bias filter. The here described state vector now only includes the rover position and heading. If we want to describe the whole system, we should also not only store this state vector, but also all the landmarks that have been seen by some LiDAR sensor or any other optical payload. I will not go into more detail on how to detect landmarks mathematically using optical payloads, but just know that we now can, if we detected the landmarks, store them into our system state x of k together with our rover state. If the landmarks are stationary, they are not dependent on our time step variable k, and therefore are just constant. We can store up to n landmarks in our system state. This n variable will be important later because this indicates or dictates the runtime of our algorithm. Now, taking a look at our discrete system model x of k plus 1, we have a description of what happens in terms of robot state depending on control inputs u of k. In addition to the control input, we also have process noise. Taking all the previous formulas into consideration, we can now put them into our f. F is then including our rover position x of k and y of k, not to be confused with our state x of k, and also our steering angle, heading, and wheelbase. As previously described, wheelbase being the distance between front and rear axis of the rover. The function d of k is used for simplicity and describes the distance traveled. It's v of k times delta t. So velocity multiplied by time. Now let's take a look at our state space equation for our system model. The state space equation, which under the assumption of a linear system can be modeled as a first order differential equation. In this case, we see x of k plus 1, and x of k plus 1 equals a multiplication of our state transition matrix times the state, in addition to our control matrix times the control input, and also in addition to our process noise. Inputting the previous formulas, we now receive our state space equation for our position and also for our heading. Since the Kalman filter uses probability to optimally estimate and correct states, we need the error covariance matrix P, which represents the uncertainty of previously described state estimates. The matrix Q in this case represents the covariance matrix of the process noise. Also, the state transition matrix is used again to calculate the new error covariance matrix from the old one. Now, taking a look at the definition of the covariance matrix, we see the variance of each state variable being the squared standard deviation on the diagonal, and on the off diagonal we see elements that are defined as correlation coefficients, where the standard deviation of two state variables is correlated. How to calculate those off-diagonal elements you can see in the equation on the bottom right, using their standard deviations. The next step is to bring our optical payload, in our case a laser sensor, into the calculation. Therefore, we relate our measured observables to the state vector x. This is done by multiplying a measurement observation Jacobian with our state vector x of k, and also adding measurement noise w of k. Z of k is a two-dimensional vector that includes r of k, which is the range distance, and gamma of k, the relative bearing to landmarks measured by the sensor. Those two geometric functions can be calculated the following. R of k requires measured x and y values and the location of the sensor on the vehicle, in addition to a measurement error. Gamma of k also needs those values, but also the orientation of the robot indicated by variable phi. As you can see, the sensor position in x and y coordinates is a time-dependent function. Those two functions can be calculated by using the two constants a and b, which describe the sensor offset from the rear axis in x and y direction. Now let's take a look at our state equation of rover motion. We start with our rover's pose, which can be defined as a three-dimensional vector with x and y describing the position and phi the heading. If we now derive this by the steering angle, we get the following equation. This formula is only correct under the assumption that our rover maneuvers are based on Ackermann steering. Rover motion in x and y direction can now be described with the wheel radius and also the heading, and our heading can be described by using the wheel radius and the half-axis distance and also our control input. This control input can be calculated by using the average differential wheel rotations of left and right wheel, omega L and omega R. Since our process is not noise-free, we also have to add the process noise W of omega to this calculation. For the case that our rover is turning in place, the changes in x and y direction become zero. Of course, our estimation error covariance matrix also changes over time, and its derivation by the steering angle holds the following. F being our current transition equation and Q being our covariance matrix of the process noise. This leads us to our update equation of our a priori covariance matrix. Next, we have to update our rover state. Our previous rover state is added to a weighted difference between state measurement and also state estimate. How much this difference weighs is decided by the Kalman gain. For a high Kalman gain, more recent measurements are to be weighed more than older ones. This leads to faster responses, but also leads to our output not being as smooth. Our innovation thus can be computed by taking our difference between prediction and observation. Our innovation, of course, also has a covariance matrix which tells us how much we can trust our innovation. Now let's get to our finally updated state estimate. This can be calculated again with all previous formulas, and we are taking our a posteriori state estimate and adding it to our weighted innovation, and our weight is defined by our Kalman gain. The error covariance matrix of this updated state estimate tells us how much our measurement deviates from the prediction. It is calculated by taking our a priori estimation covariance matrix and subtracting it by our weighted innovation covariance matrix. The weighting factor, of course, is again the Kalman gain. It should be noted that using our raw pose data, like in the example, in our states with x and y and also with our heading is not optimal. And for real applications, quaternions should be used to further decrease computational complexity. Talking about computational complexity, because we are storing our landmarks in our state vectors, we can get really high computational power requirements. Maintaining our covariance matrices and multiplying matrices takes up O of n squared, with our bottleneck being matrix inversion, which takes O of n to the power of 2.4. This is a really pessimistic worst case. In the reality, we should decrease the number of landmarks used in our calculation. This picture from the book describes this process pretty well. Old landmarks lying behind our rover are not taken into consideration anymore. Only previously discovered landmarks that lie ahead of our rover in a certain radius are used in our Kalman calculations. Using this technique, we can decrease n depending on our computational boundaries. Other very popular solutions for SLAM are firstly particle filter-based SLAM, or also called fast SLAM, which also is based on bias filters, but has the advantage of not being limited to Gaussians, and graph-based SLAM, which is using graph theory to solve the problems presented by SLAM. On particle filter-based SLAM or fast SLAM, there's also a chapter in the book, which is covered in another video. This now brings us to the end of this video. Thank you for watching.